Okay, welcome to the second double slit experiment lecture on Physics X, Extraordinary Concepts in Physics. This time we're going to do a lot of even stranger double slit experiments. So if you were able to guess the results of all the experiments in double slit 1, well, you might not be able to get them all this time, but even the next two ones after this, extraordinary double slit experiments, they're going to be even stranger yet. They'll still be relatively simple though, so I think they're going to be fun, so play along, please. So this is Physics X, the coolest concepts in physics explained with minimal math, trying to focus in on the concepts. This is actually being taught for credit at Michigan Tech. There is a studio audience here, some of which will be getting credit. No textbook is required. If you're just surfing along on the web, welcome. I think we're available on iTunes, but we're also available even if you don't have iTunes, just through the Starship Asterisk bulletin board, which anyone can see. It's just a bulletin board where people discuss things like the astronomy picture of the day. And if you can make this out, although the font went really small, then you can go there and just click on that, and you can get astronomy lectures free without a textbook, and physics lectures like this free without a textbook. So let's go into more and stranger experiments. So let's now take the same double slit experiment, and this time we're going to substitute in gamma rays for the photons. We're going to bring in a gamma ray source. So this means that the wavelength of the photons is now much smaller than the width of the slits and the distance between the slits. So here you have a gamma ray source, gamma, gamma, gamma. Here you have double slits. And here you have, this is the slit screen here. This is the image screen. So you can say the gamma rays, when they hit the image screen, they still create a spot. So what happens when you replace normal photons that we would be able to see in the usual visible range with gamma rays? Do you still get an interference pattern? Do you get no interference pattern? Does the image screen remain blank? Or does a safety inspector insist that you need a permit? Which of those would happen? Please consider that. Change to gamma rays. Do gamma rays matter? All right, so the answer to that is that no interference pattern appears that you can tell. Now some people will say, well, there's always going to be a tiny little bit of diffraction. You're going to have a small amount. Well, maybe. But for the most part, no, you're not going to be able to detect an interference pattern. Gamma rays are very small. They're very small wavelength. The distance here is very small. They're very powerful. They go through your bones, which is why they're more powerful than X-rays, which are stopped by bones. So they plow through the slits without significant interference. Therefore, the image screen will show a bright band behind each slit. So what you will see is, so here's the gamma rays. Again, here's the double slits. Here's the slit screen. Here's the image screen, if I can spell. So you just get the gamma rays just plow straight through, and on this screen here, you just get two blips of brightness behind essentially the geometric projection of the two slits onto the image screen. So you're not going to see much. So if you go too powerful, it just won't work. But people are curious about that. I was. So here I have a different kind of concept that I'm exploring called a slider, because people have sliders on their screens like this, and they can click on them and move them up and down, and things change. Well, let's say you had a slider where you can change the wavelength of the photons. Let's say you can decrease it from the gamma rays down to the visible light. What would happen? Well, the light would redden, even though it might not be necessarily red. It would move from gamma rays to X-rays to ultraviolet to the visible range, the optical range. The diffraction now would increase. So as you go down, you now get these things. Instead of being projected out like this, they are now, let's see if I can try another color at the same time, they now spread out more. So the more they spread out, the more overlap there is, and the more chance there's going to be significant interference. Interference peaks will move further apart and eventually become discernible because the gamma rays are so close together they start out not being discernible. So that's how you move into the range. Eventually these things are really wide. Let's try a new color. Let's try purple. Eventually each one is extremely wide and most of it is overlap. And so you get an interference pattern. Let's go back to blue. Okay, so we got that one. Let's go the other way. Radio waves. Everybody's heard radio waves, at least through the device in your car. So you take the same double slit experiment. Everything's the same. We're going to learn by changing out one thing and seeing what happens. We're going to change out the photons to now be radio waves. Now radio waves, so if this is regular visible light photons, the radio waves, I guess they would be down toward the red end, they would be much longer wavelengths. Okay? Notice I used red. I went the right direction. Now what would happen now if you put radio waves through a double slit experiment? Would you now see an interference pattern? Would there be no interference pattern? Would the image remain blank? Or would a song play that's a little bit too noisy to be a hit? Think about it. What would that be? You might notice that many times I take the fourth one and throw in just a little bit of an attempt at comedy there. Levity. But bump. Image screen remains blank. Now is it perfectly blank? Well, maybe, remember you're not allowed to go through the, you're not allowed to go through here. So is there some chance that some radio waves will leak through here? Yeah, maybe one occasionally depending on the wavelength of the radio waves and the width of the slit, but practically you're not going to get anything through there. The little holes in your slit screen are not going to allow radio waves to get through in any significant amount. So you're just going to get blankness there. So the people waiting at the image screen will be waiting there saying, hey, waiting for the photons, nothing's coming. Because it's all blocked by the slit screen, in this case, with radio waves. So let's go back to our slider and talk about lambda, which I forgot to use the Greek letter. As lambda increases, the light reddens now from optical to radio waves. The diffraction increases, concentrating less light behind each slit, as was explained a couple of slits ago. The interference peaks move further apart and eventually disappear. Okay, so maybe you learned a little bit there. So let's keep changing stuff and see what happens with this two-slit experiment. Let's try to understand the most fundamental experiment in quantum mechanics by changing one thing out and seeing what happens. So now let's say, here's a good one. The double slit experiment is done, except a light bulb is used emitting many colors all at the same time. What happens? So now you have a light bulb. And I guess it would have to be one of those fluorescent lights to save energy. It's hard to get a regular light bulb these days, an old-fashioned incandescent bulb. So this light bulb is emitting all different colors, and I can do that for you because it's the future. There we go. Black's an interesting one. I don't know how that works, but we'll put that on there anyway. So you get all kinds of colors going there, and they hit the double slit, then something hits the screen. What do you see? Do you see an interference pattern? Do you see no interference pattern? Do you see interference for different colors appearing with different spacings? Or do you see psychedelic? Do you hear psychedelic music begin to play with all these different colors, man? Interference for different colors appears with different spacings. As you would have guessed from we talked about the radio waves and the gamma rays, you get different spacings. It depends on the wavelength here. And supposedly for one different lambda, which we're calibrating thing, all the photons have the same wavelength. So different colors of light will have different wavelengths, and each of these colors will interfere. Each of them will. But they'll all interfere with slightly different spacings. So usually my experience is you can actually make out an interference pattern. Possibly if you had one type of light source, it would seem to wash out and it would seem mostly white. But there would be interference there. And if you had it right, you could see the different colors interfering at different spots, different distances. Okay, so let's try another one. Now let's say you have a color filter placed over one slit. So here you have your basic slit screen, and here's your image screen. So this is slit screen. This is image screen. So now we're going to put over one a red filter right behind it, or you can put it in front of it. Redness. Now you're going to let your white light source that has all these different colors come out here. Let's do all the colors of the rainbow here, or as many as they'll let me do. By contract with the company, I have to do all the colors, including black. Okay, so what happens here? What do we see at the image screen? What happens here? Oops, then I have black. Hello. Do you see an interference pattern? No interference pattern? Only red light interferes, or only red lights avoids interfering? Think about it. You can whisper, you can hum Jeopardy music to yourself. Okay. Bada bing. Only the red light interferes, because that's the only one that's going through both slits. So the blue light, so if you look through like a red filter or a red balloon, the world looks red to you because all the other colors aren't getting through. So only the red light is going through both slits. So it's only the red light that's going to interfere. The other light was stopped by one of the slits, and therefore it can't interfere. And it's going to go through the one slit it can go through and just illuminate the screen there. Okay. So now we're going to place a wall between an opaque wall from the source to the slit. So now we're going to have a, let's do it in blue, I like that better. So here we have the source here, now considered a monochromatic source. But now what we're going to do is we're going to put up a wall right here and say nothing goes there. What happens, what do you see here when you put up a wall? Do you see an interference pattern? Do you see no interference pattern? Does the image screen remain blank, or does the wall become radioactive? So now, if there are photons trying to talk here, they can't because there's an opaque wall there. What happens? We're running out of time, so I will tell you a normal interference pattern occurs. You don't get any change. That's because on the far side of the image screen, over here, there's all kinds of room for these things to interfere between the image screen and the slit screen and the image screen. Also, if you were at this, one of the key things is which way information. So if you have this blocked here, it doesn't tell you which slit the photon went through. How it went from the source to the slit is irrelevant. What happens in reconstructing which way information, and we will find that if you have which way information, which slit each photon went through, then that may destroy the interference pattern, strangely enough. So stay tuned to hear about that. But if you can't, then you get an interference pattern. All right, I'm at my 2-minute warning, so I will go to what happens now if you have an image. So here's a slit screen, image screen. Now you put an opaque wall from here. So here's your source. Now you have an opaque wall between the slit screen and the image screen. What happens then? What do you see on the image screen? Do you still see an interference pattern? Do you see no interference pattern? Or does this wall make strange barking noises? So here, I have to hurry because I'm running low on time. No interference patterns occurs. If you put your, I should have kept the thing. If you put the screen here, then you can tell which slit the photons go through. Once you know which slit the photons go through, you destroy the interference pattern. So you get a brightness here and you get brightness there, but you don't see the interference maxima and minima, because now you can tell which slit the photons went through. So that wall does make a difference. So we're not always saying interference. Last, now let's say you have two identical point sources replacing the slits. So instead of having a slit screen, you now have two sources. And now you have an image screen here. And you bought these sources from the same catalog. What happens? Do you get an interference pattern here? Do you get no interference pattern here? Or do you get sometimes an interference pattern that is visible, sometimes it's not? Or can only identical twins know the answer? And so we're running really low on time, so please pause it because this is a cool one. The answer is that sometimes there's an interference pattern and sometimes there's not. And this is a strange one. That's because even if you have two sources that you bought from the same amount that have the same, they might not remain coherent for very long periods of time. For the vague amounts of time that they do, you might see interference patterns shift on the screen. Is this in conflict with Dirac's particles only interfere with themselves quote? And the answer is possibly, but it's still debated. I'm not 100% clear, so that's reached my level of misunderstanding quantum mechanics. I can't clearly answer that question. Some people might be able to. I'm still checking it out. But we're going to have lots more of really fun stuff next time. So please join us next time for extraordinary double slit experiments. Thank you.